Okay, hi everyone. Welcome to Lisp Study Group. My apologies for the late start today. Fortunately, a couple of things came up that ended up requiring my attention. But today we're going to be continuing our discussion on method combinations. Last week, as many of you saw, I decided to kind of explore method combinations a little bit more in detail than what we've done in the past, mainly to give, and I provided kind of an overview of what method combinations are, as well as both what's called the long form description of a method combination and the short form description of a method combination, where the short form and the long form both require you to use defined method combination to actually go in and specify what that combination is, and with the short form being one where we are explicitly just saying what operator we're using to create the method combination with, and whether or not there is an identity function with one argument, whereas when you're using the method combination and you only have one method in your method combination that uses this, then it does some additional checks just to make sure that it can get invoked without throwing an exception saying that there isn't more than one as part of this. Um, We've ended last week's conversation with kind of a discussion on this case study that I was thinking about, which is um, implementing a method combination for an lparallel like workflow dispatch. And I had realized that in order for me to kind of do so, I would kind of also have to introduce lparallel for this discussion. So I thought that I would go ahead and do that today, just so that when I do go ahead and implement L parallels um, workflows inside of this method combination that we're doing as a task, I don't have to necessarily have to explain what the library actually does. It'll give you guys a chance to actually use it and see what I'm using it for without having to worry about, well, what is this third party library is and so forth. So to begin with, I thought I'd just, kind of go through as a prerequisite as what lparallel is. For folks who are watching the stream right now on YouTube, yes, the, the name says exploring method combinations, but I will actually rename the YouTube video later on after our stream. Um, so what is lparallel? So many of you know that in terms of different common lists, that the way of doing multi-threading is this thing called Bordeaux threads, whereas you can actually dispatch a thread using what's called BT make thread. It will take in a function that will allow you to go in and invoke a different thread of execution. The thread of execution will go and run the function and return some sort of result, oftentimes a void, because at the time that threads and Bordeaux threads were created, threads were supposed to be essentially the equivalent of processes, usually processes having either a error code and in return of some sort, or some sort of crash, but it doesn't necessarily actually share data like a function call back to its parent thread. Um, so with Bordeaux threads, you had this ability to then do some sort of concurrency by able to run different threads of execution. Obviously, scheduling was not kind of something as part of that mix. Um, and you were able to do what's called shared memory multiprocessing or shared memory multi-threading programming, where you could use condition variables, mutexes, and other mutual exclusion types primitives to actually go in and share memory and share data between threads of execution and be able to actually, run concurrent code. But that's one form of concurrency, obviously. You want to be able to do like task level parallelism and expressing different types of like parallelism at different levels of granularity. Additionally, you want obviously when an exception is actually kind of thrown, although the thread through the exception, because the exception that's being thrown, or in this case, since we're talking about common Lisp, the condition that's being thrown, that actually ends up requiring you to stay within the thread. It doesn't actually throw across threads. Sometimes there's information that you need to actually pass over, that the only way that you can do so is upon the exception being thrown at the top level where you're catching the exception, or in this case, condition. In your condition handler, you share some error or some information across of what's in the thread of execution in a variable that can then be seen across threads through the use of a essentially a critical section. You're using a some sort of mutex lock to access the actual error code and be able to actually retrieve its information and do some sort of decision making. So what lparallel did is it created kind of a library to express some of these different types of what we'd consider traditional problems in parallel programming, all right? And I'm saying parallel versus concurrent because most people think concurrent and parallel are synonyms, but they're not. Concurrent is more of non-deterministic um, execution, so we don't necessarily know whether or not a thread um, it will fail on success or failure. We just kind of expect it to do some sort of task, um, and we let it go off on its own, and then let it complete the task independent of the actual execution of the program. Whereas with parallelism, you have different types of parallelism where you want things running simultaneously. In some situations, you may want to run a bunch of stuff simultaneously and wait until all um, parallel tasks are completed to a certain things and check their results before moving on to the next stage. This is something called barrier synchronization. And lparallel provides a lot of primitives for doing these kinds of like parallelizing tasks. So it has parallel versions of map, reduce, sort, remove, filter, and others. It has a version of doing condition handling across thread boundaries. It has the ability to actually be able to do um, uh, this kind of fine level parallelism that we're talking about, and it has some other data structures for talking about priority killing tasks and so forth, and things like integrated timeouts and other data structures and stuff. So this is a pretty useful library to kind of know. This is available as far as I know. I've got to go. I did not check this before the stream. Um, on it should be available through Quick Lisp, which it looks like it is. So let's go ahead and load up lparallel and we can get started. And I'll add this to my project at some point too. Oh, right, because I accidentally put a quote at the end. That was by mistake. There we go. So, um, let me just do one thing. When you first install lparallel, one of the nice things to check to see is whether or not it got installed and you have full support for it is running the test suite that it has. I'm not going to run it right now. I'm hoping that it kind of works. But if you read the docs, it'll actually tell you that you may want to actually go ahead and execute this, and then you have different types of ways of also running it because they have benchmarks associated with the ability to uh, run certain tasks on a particular operating system. The core of lparallel's library is this concept called a kernel. The kernel is your scheduler that will actual deal with your task scheduling. When you register a task in this kernel, you can actually go ahead and uh, execute it inside a bunch of worker threads. Usually, what ends up happening is in a multi-core machine, such as most modern processors are, although lparallel was written in time and in single processor, so it does support single processor multi-threading too as well. It will create a thread pool for you. Usually the thread pool being the size of the number of cores that you have, plus probably hyper-threading turned on, although I haven't actually experimented with that. Um, and what it does is it will actually go ahead and um, use this thread pool to actually run your tasks in independent of the actual parent level Lisp process. Okay. Um, for folks who are on the Jitsi call as well as anybody um, on the live stream, just feel free to ping and write your questions and I'll answer them accordingly. So there was a question here. Um, okay, so there was a general question about. Oh, okay. So I'll go ahead and ignore that. Okay. The one of our my patrons on the Jitsi channel had a question that I thought I needed to answer, but it's okay. It looks like I can ignore it. Um, so let me just do something here. Here we go. So let's go ahead and start up one of these threads. One of the things to note is, and I'm gonna just show this to you. The main thing to start a kernel is essentially something called make kernel. If we look at make kernel's documentation here, which I'd like to show, they have it here. You could see, oh, sorry, I forgot to mention that it's also a function. You can see that the argument that we're providing is a number of workers that we need to do to create the thread pool. Okay, let's go ahead for this type of kernel. Let's create a help parallel. Actually, let me go ahead and put this in my buffer here. Parallel kernel. Okay. So lparallel has this top level kernel object that you could think of as being the singleton of your thread pool. When you start these applications, ideally you want to actually go ahead and set this global variable, and we do that through what we saw earlier, which is make kernel. If I can type in make kernel, and we specify the number of threads that we want, and I'm going to go for the time being as being 10 threads. Okay. So now we have our threads that we can actually run stuff on, and we can actually go ahead and start um, talking about tasks. Okay. Um, one thing to note about kernels is that their lifetime is usually the lifetime of the Lisp session that you're running. So as long as the Lisp process is running, your kernels is running. Um, You can have different kernels running at different times and schedule them yourselves. So essentially having different thread pools for different tasks, and then each one of these can easily be changed by changing the dynamic variable that I just showed you earlier. The you just need to set f that kernel object, and you've effectively changed where the rest of the API is going to dispatch their tasks to. So um, one way of thinking about this from a flexibility standpoint is you could use a closure to change the thread pool before you actually call any of the specific L parallel tasks in a way to be able to do, say, um, a higher level version um, of scheduling than what is normally typically available, where you end up trying to use different tasks with different metadata and having a single thread pool kind of distinguish between the two, as you would in other modern languages. What is a task? A task is nothing more than just a function. Okay, there are a couple things to note about what a task does, um, and the main thing to know is uh, that you could create and execute tasks using something called channels. All right. These channels essentially are what's it? These channels you could think of as more like thread invokes. So like basically when you say um, uh, run this task on this channel, you are actually having the channel dispatch to the underlying thread pool a particular function and function call. And the way you do this is you need to start by first creating a channel, right? Which we could do by just creating, hold on 1 second, not Chanel channel, by calling make channel. And make channel, please note, there are some stuff that you could do, like there's buffered tasks you could do, but for now, we're making a unbuffered channel for the time being, okay? So now that we have a channel, just like most CSP-based systems, all right, although this is not communicating sequential processes, please make note of that. The channel is just nothing more than a conduit to actually go in and make requests to the underlying kernel thread pool. Um, to put things into context for most people looking at this from coming from more languages like Go or even Rust or even more recent languages that started supporting channel the channel data structures and Go routines. lparallel was created, if I remember correctly. My dates might be a little fuzzy. Think about 17 years ago. It's about 2007, 2008 that I vaguely remember that I first saw L Parallel. It's obviously improved since then, but this is roughly around the time that CSP started becoming more of a way of dealing with concurrency. And this is also around the time that Go first came out because to actually address some of this to create some of these things. So a lot of these ideas were up in the air, but this particular naming of the data structure is more of talking about the pipe to talk to the thread pool to execute stuff and then receive results of it. Once you have the channel, you can actually go ahead and submit stuff to the underlying kernel, which again, as you can see, since we've set the global variable star kernel in L parallel, we don't have to go and pass the kernel upon which we're trying to schedule stuff anymore. We can just use the API as is. We'll just use submit task to actually go ahead and talk to this channel that we've created. We specify the function that we need to create. Now, this function call is not going to be what most people are going to use this notation. No, you need to use the quoted notation to pass in the function. It will actually go ahead and just deal with it. The hash bang, the hash quote that most people are familiar with and actually talking to other stuff is not going to be required when you're talking to the channel. I'll show you what happens when you use the hash quote later on. Once you pass in this, you're not actually taking in a lambda. That's okay. And you could certainly do that, by the way, and I'll show that in a second. In a second, but it's not an S expression. It's not actually what you would normally see. So it's not like you are creating in like Bordeaux threads when you're making the thread, you would actually pass in a closure that will take in the lambda and whatever arguments that you want to pass in, and then it'll execute it that way. What you're doing is you're passing in the actual function symbol, or in the lambda case, the lambda form, and then the arguments are specified separately. So in this case, we're passing in L parallel submit task, and what we're going to do is we're going to go ahead and print by grabbing the result, okay, from the channel, and we're just going to print this guy. So this code here reaches out to the thread pool, calls channel, computes the addition of 3 and 4, and then when we receive the result, or whenever we receive the result, we're receiving it in this case immediately, we'll go ahead and print it out, okay? And when we run this, you see that we actually end up getting 7, okay? If you don't actually receive the result, the message is going to just sit there. Um, you, I haven't seen anything regarding um, dropping results when I played around with this. Um, so for this case, we're just gonna go ahead and uh, uh, deal with it, as is. Now you can also do um, in the same realm. okay, multiple requests to the task. So, and let's just take the example of two things. One is let's pass in submit task channel, the lambda function. Okay, and in this case, we're just going to say we're going to just return hello. Okay, we're not going to even do a computation. Okay, the first time it's going to run, it's going to return 7. The second time we run it, we end up getting um, hello. Okay. Um, so actually, let me just clear this REPL just so that you guys can see this again, because I noticed that my previous results kind of confuses the issue. It didn't put a new line in between the two. Notice the order in which things are getting returned. Because of the fact that the last task is obviously hello, you're going to end up getting a the last task execution is the first one that's actually going to be returned in a so it's essentially a LIFO um, style stack that's going to actually run your execution. But let's say that we don't actually receive anything from the result and we just do this. Well, in this case, the channel doesn't hold any results. It looks like we are actually going to go ahead and drop um, the the pro, the results from the previous one, and we could totally see that by running this multiple times, and we'll see that it will always only return whatever is in um, the whatever is not in the channel. Um, but let's try and do one more thing, which is uh, let's create a separate global channel. All right. And I'm only doing this for illustrative purposes. This is really, I think the closure approach is the correct thing to do. But just to show you what happens when we use the channel. Okay. And then let's go ahead and hold on, run that. Ooh, wait, what was it complaining about? Warning, oh, that's right. That's because I'm using setf before I def parameter. All right. Okay. So now let's go ahead and do lparallel submit task channel 5 and 6 and um, hello world. Okay. Now, when we run both of these here, we now have two results that are going to be stored in our channel. Okay. And when we look at the channel, we actually can see that the list of results that it's currently inside of it in head and tail. Okay. When we run, say, receive result, okay, parallel, sorry, receive result, and we get 30, what happens to our thing? We pop it off, okay, because of the fact that in this case, submit task ran first, hello ran second. So Uh, the order in which it actually received the results is slightly different. So the head of it is actually, oh, this is actually run out creating, this is weird. Hold on one second. In this case, we saw, this is this is what I expected, which is the FIFO queue because in the our parallel documentation mentioned it was a FIFO cube. But if I do this, this is printing hello first and then 7. That's weird. Um, okay, I'm gonna make a note of this. It looks like there's a slight behavior difference when you're running it as a closure versus has a separately in a non-closure fashion. Um, okay, so when we run this and we actually receive the result, you can see that we're still caching the results of um, the channels. All right, let's go ahead and run this one more time, and we see that the channel is empty. Okay, now if you try to run lparallel receive result again on an empty object, you end up getting this blocking call. You don't actually get an exception. Okay, um, so saying that it's empty, it's actually waiting for the next result to actually to happen. Okay, now to reduce this, there isn't any clear way of just doing a non-blocking stuff. This isn't asynchronous in that sense, but it is something that is um, to be aware of. So uh, on empty calls, it actually is just going to just stick around. Right, you can end up, potentially blocking your Lisp session. So um, don't don't do what I did at home unless you have a clear reason to actually block and wait for the next result in a separate thread. Each task inside of your task queue has a priority. All right, um, and so um, that priority can then be used to actually change how things are going to get executed. Um, the default priority is obviously default, and then you can actually have a low priority as well. Um, just to show you an example of this, you have the ability to say, let's say that we take this guy here and say, and we want this to run as a lower priority than hello world. So what we could do is we could do here, and we could take lparallel, I think it's called task priority, and we could set that to being low, and then we can execute our current job here, and then we can run lambda first. Let's see how this actually changes the execution of our channel. We could see immediately when we look at the internals, right, that in our our queue, because we made the task priority being low on the first task, the second one actually ended up getting executed um, first, the second task, as we expected it to. All right. And you can use this to actually go and do priority-based task execution. Okay. Please note that in terms of types, clearly, as you can see, since this is where we have a heterogeneous list here in head, um, that the task objects themselves are isolated enough that you can, and that we don't worry about the actual underlying type of the value that's being returned from the task-based queue. So if you wanted to actually have some level of type safety at the task level, this certainly doesn't give you the ability to have a single type across multiple things for a single queue. This is something that I want you to keep that in mind. This is very generic enough for you to actually be able to handle that. Um, if you wanted to actually throw out your thread pool, and this is something that I want to kind of move on, you can actually go ahead and get your kernel to be uh, uh, garbage collected by simply running set, I think it's lparallel end kernel, and this guy will actually go ahead and clean up all your threads, all right, and have them garbage collected. In this case, you could see that in that our thread pool of 10 threads are all basically shut down. Um, and we actually underlyingly are using SB thread, which is actually Bordeaux threads too as well, to actually run some stuff on top of lparallel. Okay. Are there questions about this? Just check. Okay. All right. Before I move on, I want to also mention one other thing about this project, just because this is something that I haven't had a chance to really dig down into and play around with, but this is something that is a natural extension once we start doing this kind of work with lparallel. And that is that the notion of the kernel um, and the task scheduling paradigm that lparallel provided has actually been extended to work across um, different um, machines using something called lfarm, which is an extension of this API. And the only difference between lfarm and lparallel is that with lfarm, you end up having to create um, your servers first, and then you can create a single kernel that actually extends lparallel's kernel before you start using lparallel's API on lfarm, and then you have an abstraction that now works from single machine to multiple machines. So essentially, what these two libraries in consort does is using the same code base. The only difference between running something on a distributed cluster and running something on a single cluster is changing the object construction of your kernel, and that's it. You don't have to do anything extra to actually do this. And later on, this paradigm that I'm bringing up to you, and I'm going to reiterate this when we do that example. Um, you'll see that simplicity make things a lot easier for you to actually write distributed programs from parallel programs. One thing to note about, and I've completely forgotten about this, and that is about handlers that we saw earlier when with the blocking handler. Let me go and restart my thread pool, and let me talk about handlers a little bit. Okay. What is a handler? A handler is essentially your condition handlers for that a task can necessarily throw for a particular condition. So we'll talk more about this in two sections, but basically I wanted to mention um, handlers. Tasks can signal conditions. Conditions can be handled by handlers like we would normally do in Common Lisp. But if an error from a task goes unhandled, so if we throw a condition from a task that's being executed and there isn't a corresponding handler for that condition, what ends up happening is our underlying infrastructure does not stop execution or throw an exception or anything, because again, we talked about this with threads. We don't actually necessarily, because each thread is independent of each other, we don't necessarily throw up an exception to the top level REPL to have it handle stuff. It might end up just being ignored. So what happens is that in this case, there's a default handler that at the farm level that basically takes that condition object and it actually creates an arrow info object that is then placed into the channel um, of the task that it was executing for. And um, once you receive that object, that arrow info object, then behind the scenes, the infrastructure will go ahead and signal the error. It'll throw the exception behind the scenes when it receives the actual error. So this is one way of throwing um, errors across boundaries. All right. As you saw pretty quickly, and you probably noticed, the channel itself um, uh, gives us some ability to communicate between threads in the thread pool for task execution and and so forth. But if you want to actually pass information between um, your channel, so your actual underlying code and your channel, sorry, your task, then in that case, you want to have some sort of blocking data structure to uh, do essentially the equivalent of shared memory multi-processing, right? We could do this with lparallel with a couple of already predefined data structures, one of which I've mentioned before earlier when I was talking about the library, and that is the blocking queue. Um, the a queue that essentially has the equivalent of a lock um, at your disposal, and it can be just used to actually go ahead and um, pass information to an underlying task that's looking into that particular queue. Okay, so let's see an example of this. So let's go ahead and create our queue. Why is make queue not showing up? MK. Did I see this? Did they change this? For some reason, it doesn't look like this is showing up. You may not have exported this guy. Let's see what happened with. Mm, Gecko stream make channel. That's a process tree. It's not what I wanted. Hold on. I think I might be looking at the ah, right. So I have to go in order for me to use this blocking queue, I forgot that I have to add one more library here, which is actually, let me see if this is already available. It should be part of regular one. Yeah, there we go. So make queue is part of the lparallel queue package, and I wasn't sure that it was part of the ASD that I currently loaded or not. So let's go ahead and run this with the make channel. Okay, so we now have our queue and our channel. And what we're going to do is now we're going to go ahead and submit task with task on our channel, the lambda function that print pop q. So lpar q pop q q. Okay, and let's go ahead and also add one more Oh, right. This is not going to, let's do this. Um, BCP slurp forward. Okay, here we go. PopQ. So what we're going to do is we're going to go ahead and return this as a list. We're going to grab the two items that I'm going to push onto it as a result. Okay, and then we're just going to go ahead and uh, receive the result. Now, one thing to note is um, when we first call popq here, it's going to wait until we call a corresponding push queue. It's just going to sit there until something happens. So if I ran this as it is, it's just going to wait. My Lisp session is just going to wait, and there wouldn't be a way for me to actually continue to run stuff over it. So what I have to do is I have to run essentially lparallel dot q dot push q, and I'm gonna just run hello, and let's go ahead and run world, and let's go ahead and print the result that it's going to get from our channel. All right, so we end up getting that. So when you run this, you end up seeing that we popped it the first time, we get hello. Popped it the second time, we get hello. Now Lambda can actually complete the execution of list, um, and it will return from that function, put that result in our underlying receive queue on the channel, and then we get the result. Notice in all of this, there isn't a damn lock. Internally, there are probably some mutexes to handle the sharing. More than likely, there is. All right, but we can safely ignore some of that stuff because we are using these underlying data structures to communicate between L parallels, thread queue, and our stuff. And the conduit, the channel, is the way of communication between the two. This is the beauty of this library, and it's one of the reasons why I was kind of curious about essentially wrapping this up into kind of a method combination of this. All right. Now, I don't want to spend more time on this. This one other thing that I wanted to bring up, and then I'll just quickly run through some of the other stuff that's available on this. But this is a very brief overview for the cases of that we're going to be talking about as we move on with our case study. Um, One thing that I wanted to bring up is the stuff that you saw with the dynamic variable bindings. Ha- Most folks who are familiar with common Lisp would know this, but I'm going to assume that you're not so much familiar with the underlying context about dynamic variables and that are dynamically bound. All right. Um, but when you bind a dynamic variable dynamically in let's say a lexical closure, all right, and an example of this is something we saw earlier when we were doing task priority. That is actually localized to the thread. So in this way, the dynamic variable can be used as a way of doing what other languages call thread local storage. All right, that is essentially have state that is localized within a thread that other threads cannot have access to. Okay. Um, the underlying, it's surprising for most folks seeing this from other languages, mainly because of the fact that in most other languages, the global variable is a global variable, right? Um, But in this case, the variable name, the star, the earmuffed variable, all right, that's what's shared across multiple threads. But how it's bound is actually localized. What it's actually bound to, the value that it's about bound to, that's what's thread localized, all right? Um, this might take a little bit getting used to coming from other languages, but that is something that I'm gonna kind of bring up again. Um, we kind of quickly touch based on dynamic variables, but one thing to note is um, you can with this dynamic variables you can actually do the assignment in a per task basis, which is a per thread basis or per worker basis. Okay, um, a per task basis essentially is when you run, let's say, and I'm not going to really submit this, but this is something that you could totally do is when you run lparallel submit task, let's say we put it on a channel, and then let's say that we created a lambda function internally, and then we use some uh, underlying variable called let's say our standard thing foo versus bar. Okay, and we have some go dynamic variable called foo. Right now, foo doesn't exist, so this is going to end up throwing an exception. And then we want to do something about this. Okay, you could certainly do this by, and then internally we call another thing. Let's say, um, and in here we bound now foo to whatever foo is. Okay, and then we run bar. All right, some variable bar. Here, what we've done is we've taken the, let's say, the global state, okay, in the dynamic variable foo, and we assigned it to foo, okay, and we localized it into the task itself by rebinding it to the global foo. And notice the reason why we did this is because at the point of channel execution, earmuff foo is actually a dynamic variable whose context is in the parent Lisp process. Okay, that state is not going to be messed with. Okay, but as soon as we go into this lambda function here, this inner lambda, earmuff foo is can be considered like another environment variable that you could do a set env on. Okay, so at which point, if you wanted to actually get the process variable into the local process, doing this copy now guarantees that if you mess with earmuff foo within the context of this inner lambda function, this outer earmuff foo doesn't change. Okay. I'm gonna let you dwell on that for just a minute, and see if there's any questions. Okay. Okay. Um, the reason why I bring this up is because let's say that you wanted to create thread local variables. All right. You wanted to essentially do this style of things. Well, lparallel has a nice little argument called bindings that can be passed over to your kernel, and that bindings can be used and to reestablish those thread local variables um, every time a new creator is created. Okay. Now, obviously, there are costs to this mainly because now if you have 10 creators and you are evaluating this each time a new creator is created, you're essentially running the same execution for each environment 10 times, which is fine if you're doing thread local variabilization. You're not doing any sort of initialization there. But it is something that you'd want to keep in mind. All right. That if you're trying to use some sort of complex code that needs to be initialized every time a thread is created. That complex code is going to be part of the um, underlying initialization piece of the code. So let's take an example of this. This is something that I've seen in the actual docs that I'm going to go ahead and share, and we're going to kind of go through it. But let's say you have the following code, okay? And obviously, while I'm going to correct this, this is, oops. Did I just do this? Do this. Okay, good. All right. So let's go ahead and walk through this. Let's say you have essentially a foo and a var. We're going to create something called a context here, okay? This context is actually used by the um what's it? Uh the underlying kernel to actually create a context to essentially uh um to essentially enter the thread and start its execution by fun calling what is actually available. Okay. Now, how does this actually work within this example? I think this is probably very important to kind of understand. Here, what we're doing is, let's say that you have two variables, foo and bar. This here, okay, where we are essentially grabbing bar and foo, which are dynamic variables at the top level, okay, and we're entering the worker loop, okay, which we've defined inside the uh, the worker like context, okay, and what we did is we're establishing a thread pool of two threads in which in the bindings, foo, the global variable foo, earmuff foo, is reestablished with the initial value 99. Okay. Now, what happens is when my worker context gets invoked, and that's only invoked when um, lparallel is inside each worker. All right, that's part of its task pool. And it actually does is it takes the bindings of the thread local variables and then it uses them inside of it. Okay. So let's see what this does. Okay. When we create, let's go ahead and first create these two things here. And let's go ahead and grab this guy, which is going into um, our worker context. Okay. And let's create our thread pool. Okay. Which seems to have, oh, sorry, I forgot to add here, lparallel make kernel. All right, here we know if we go in, sorry, print this, we get 0, 1 because we haven't done anything yet. Okay. In this case, though, is we're taking the kernel, okay, which is my kernel. Okay, and we're creating a channel for it. And what we're doing is we're submitting in this channel inside this my kernel the following function foo and bar. All right, and then we're going to receive the result from the channel. Okay, so you might be thinking, well, what do you think the absolute results in this of this execution is going to be? If you're thinking that this is going to be 0 and 1, you would actually be incorrect. All right, um, because um, well, let me just show you what it does, and then we can go through it. The reason why you're getting 99 and 100 instead of 0 and 1 is because inside the task pool, when submit task gets this lambda function, it invokes my worker context. And my worker context now has established that Irma foo is no longer 0. Irma foo is actually 99. So when bar gets recomputed in line 113, bar is actually doing an increment on 99 and not um, uh, 0. So that's why bar gets 100 and you end up getting this foo and bar. All right. So this thread localization piece is a very, very useful thing. And with context functions and being able to set up environments, this is where this this ability to take these earmuffed variables to use thread local storage becomes useful. All right. But this is a pattern, a typical pattern that lparallel provides for folks to actually uh, uh, share essentially initial state across multiple functions. Now, for the last 20 minutes, I'm just going to quickly go through the three kind of like functions that are available for you. Some of the rather than there's two other concepts that we can also talk about in this library. One is promises, and the other one's cognates, and I can go a little bit more into the error handling stuff. But I'm going to focus on those when we start getting into other aspects of our method combination uh, project. Okay, and the reason why I'm bringing up this method combination project is uh, is when we talk about parallel frameworks. Let's take for example MapReduce. All right, MapReduce um, and it's a very simple concept. Okay, and I'm not talking about MapReduce in terms of the functions in common Lisp map and reduce, all right? I'm talking about like MapReduce has in like the distributed framework for doing task-based parallelization. MapReduce can easily be built on top of something like say lparallel and with combination of lfarm pretty easily, pretty quickly, and could be abstracted away from a user by using method combinations where you can essentially leverage uh, the essence of task parallelization, hide the complexity of using lparallel within the method combination logic, okay, which is a macro. And then when you step out of it, um, all you are doing is essentially writing methods as part of this task-based workflow and being able to essentially implement this registration and execution, and bam, lparallel will do the rest of the work for you because we've code generated this information. Okay. Now, I know a lot of folks might be thinking that that's a little bit too much machinery for something that could be fairly simply written, has a bunch of functions, but writing all of that boilerplate is tends to what ends up being the problem. It's never done correctly sometimes. If there are new standards in terms of actually doing error handling and stuff, we ignore it and so forth. And this library and this framework, along with its cohesion and with what we were talking about before, that kind of sets the stage to be able to allow you to leverage the features of the language, mainly this ability to be able to write your own dispatching mechanism, along with existing libraries, to create a new way of actually writing a larger scale program that could be pretty well maintained over the longer time. So this is kind of where we're kind of leading towards. I'm trying to give you kind of some steps ahead, but this is kind of, I'm hoping some of you can see the magic that can actually happen as we go through some of this stuff. Um, I see there's nice comments that are um, uh, uh, Yes, to the person who made a comment about this study group going strong, I really appreciate you liking our content and joining us today. Um, if you have any questions, you know, feel free to let me know. And any library suggestions you want me to go and play around with, I will gladly go through it and kind of show folks some of the ropes as we going along with it. Just go ahead and post your comments on our YouTube on this YouTube video or other YouTube videos, and I actually will look forward to seeing new topics that are coming around. Um, so very quickly, as I mentioned before, there are already some predefined um, functions for you for uh, executing stuff inside of lparallels for a thread pool once you've instantiated the actual um, what's it the actual kernel using make kernel. One of which is pmap. Pmap will use Lisp data structures to be able to um, and it will actually dispatch and create those data structures for you, like our normal um, map equivalents. So you could see here, if I do, I'm just quickly creating um, a set of 10 integers, and you could see, hold on one second, I messed this up. Oops, hold on. Valid arguments, one. Okay, dead worker. Okay, hold on one second. This guy. Oops, that's right. There we go. So what you saw there is if you accidentally pass in pmap a lambda that takes no arguments and then an x, all threads throw an exception right now in the top of the Lisp REPL. Ideally, because I don't have a handler handling this right now, what's happening is the default handler is grabbing it and then throwing it up directly into the Lisp REPL, which I was surprised I didn't even manage to even pull that off. But anyway, if you have lmap, it basically is a nice replacement for map. It's the same thing is can be said for lparallel reduce. A lot of these interfaces are essentially matching um, the already available interfaces that you've seen. So map, reduce, and filter are all well-established common Lisp APIs that have their you know preset of arguments. And as you could clearly see by my mini buffer, map, pmap, preduce, and so forth also follows the same API specification, the interface specification. So the difference between a reduce and a map and a pmap and a preduce is nothing more than replacing the name in your function call. So a quick example of this, I'm just going to say our function is, let's say, um, x. Let's say, actually, why am I doing this? I could just simply do this. I'd say my function is hash bang plus. Our sequence is loop for I up to 10, um, collecting I. So we now have our things. And we're going to have, since we don't need an initial value, our initial value is usually 0. We could go ahead and run this guy, and you could see that you end up getting the same thing that you would do if you ran um, 55. And just to show you that this is really the difference between these two is me run it simply changing this from lmap p reduce to reduce, and you end up getting the same thing. All right. The differences between the sequential and the parallel version now becomes nothing more than a change of the API call that you're actually grabbing into. There are the I don't have to. I'm not going to go through all of the map variants, but if you go and look at the documentation of lparallel, it has, I think, almost all of the equivalents of the map API that's available to you. So mapcar can be switched with pmapcar, mapcan can be switched with pmapcan, and so forth. So and preduce uh, kind of the same thing. You p reduce can be simply replaced with reduce, and it has all the arguments and things that you can you can handle. But what if you wanted to actually implement your own kind of function? All right. Um, you could certainly do this by writing your own um, uh, parallel version of this. I'm not going to necessarily take some time to generate an example of this, so I'm just going to show you kind of the difference of this. Um, and I'm going to use the example that I saw in uh, the um, the docs, which is the Fibonacci example. Okay, so everybody knows fib. All right, I'm going to write the classic fib. All right, I'm not going to write. So if we do defun fib, let's see, we're doing single argument here. If we do if less than 2, then we got n. Otherwise, we do plus. So let's do this. A fib minus n1 and b fib minus n2 and plus ab. Okay, so we have that, and we know that, you can see that this is 0, okay, 1, and then you can see that it goes through or so forth. Okay. Now, we both know about this example of the Fibonacci, right? And if we naively wanted to run this, all right, we can use plet and kind of generate kind of the equivalent of this by simply copying this over here. Okay, and we're going to rename this guy to what the doc calls pfib slow. Okay, and all this is doing is using lparallel plet. Okay, I just am showing you that it's available to you. Okay, this is going to actually do, pfib slow here, pfib slow here, and we establish formatting, and we can compile this. Okay. Now, if you time this on both, let's say, the Fibonacci of our normal Fibonacci and, let's say, if we time pfib slow, you could see, and let me just try and pull this up here to kind of give you the difference here. You can see actually pfib slow is actually slower than our regular execution, okay, which is kind of weird, but it's there are a couple of ways of like kind of fixing this. Um, but really, what we'd want to do is essentially write, you know, a parallelized version of this. Okay. Um, One way of doing this is simply um, uh, you could just use like say p map reducer or something like that, but really you don't need to even do that. You could just simply create a parallel version of this. And the way you do it is to simply go and do this kind of task level partitioning at the level of the function definition. And the way we do that is doing lparallel. Simply change this from lparallel from defun to lparallel defpun. Okay. And defpun basically does nothing more than, in fact, let me just go ahead and do this. I'm going to copy this guy, Shift P, so I can show you all the changes. L parallel defpun. We're going to say that this is slow. Okay. And all the else's things going to be equal. And what defpun does is it actually does some essentially some chunking and some stuff behind the scenes. So if I'm not mistaken, this is a macro, right? And it does a lot of stuff, as you can see, in terms of bindings and setting up some stuff for setup. Um, and this is all to essentially partition the computation so that you could get better execution, okay? Now, obviously, there's still some redundant execution being here because since we're talking about Fibonacci, everyone knows that Fibonacci has, since we're not doing memoization and saving shared results, and across parallel programs, sometimes this is okay. Wasted computation for the sake of speed is necessary. Um, this actually would end up speeding things up. Okay, so we saw, you know, FB slow, pfib slow, but let's see what happens when we run pfib now on this. And you could see that we've actually, the difference between pfib slow and pfib literally is, I think, a 5x improvement. I think from 4 to 17, no, no, actually even more than that. Um, it's, we're using more CPU. Obviously, more space is technically, less space is actually also being cons because of it. Our processor cycles are also reduced. This is actually a pretty interesting discovery that I saw when you're defining parallel functions. This is all to kind of tell you that at the end of the day, def pun, when you're defining parallel algorithms, is probably what you'd want to use. It will do some more work for you, and then as long as you are leveraging the L parallel APIs to actually go in and define your functions, it will go ahead and um, you know, it'll actually do the job of actually dispatching and actually setting up stuff for task-based parallelization. Um, so that's all I had for today. Um, Honestly, it's I wanted to kind of set the stage for our next oncoming projects. Before I let you all go, couple of announcements. The early month of July, first 2 weeks of July up until July 20th, I will be unable to do the study group. I'm going to be on hiatus, so we won't have streams on that month until essentially after July 20th. Um, so next week is going to be our last week for the study group, for at least for a couple of weeks for mini vacation, so to speak. I will look forward. I will let you know more things that we'll be covering on, but we're going to keep going on this um, method combination, kind of like binge, if you will, um, just to see how far we could get and see if we could get something that looks a nice and cleaner version of, say, MapReduce. And along the ways, I might also introduce other concepts that are in L parallel and even maybe introduce L farm once I get some time to actually play around with it a little bit more. So I leave the full floor to questions, comments, Um, yes, and complaints. And they for the comment about me writing classic fib, even though I didn't want to write classic fib. I wrote classic fib just because classic fib is, I think it's easier to parallelize than memorize fib. So anyway, um,
Okay. Thank you, Ron.
thank you. And I don't see any questions from our YouTube audience. Um, I will see you guys next week. I hope you guys enjoy your days. And as usual, let me know if you guys have any topics that you are wanting me to discuss. Um,
In the weeks when you're gone, I don't know if I will or if I'll have anything, but if I did have something to present, would it be okay if I present something during those
Yes.
times?
yes, absolutely, 100%. I am not going to stop you from there. We would have to do some logistics on how to set up some of the um, yeah, let's talk after
Sounds
and
good.
let's I can we could schedule something. All right. I'd really appreciate that. That would be great.
Oh,
Um
okay.
I will I'll see you guys next week though in the meantime. And